Hi, I'm Jack Miskelly from CSIT at Queen's University Belfast, and I'd like to talk to you today about my research into memory-based physical unclonable functions. A physical unclonable function, or PUF, is a security primitive that uses low-level variation in electronic components to produce repeatable patterns unique to an item of hardware. These are like a fingerprint for the circuit and can't be replicated even by the manufacturer. The particular PUF I'll be talking about today is based on off-the-shelf DRAM memory. This is desirable because it allows us to add a layer of hardware-based security to a system using only the components already present in it without additional cost. DRAM memory is comprised of an array of capacitive cells that store the data. This PUF generates patterns based on the variation in discharge rate of those cells by manipulating low-level timing parameters. The pattern produced is unique to an individual memory module. The same setup on a different machine would produce an entirely different response. Today, I'll be demoing how we can use these kind of hardware-rooted identifiers in the use case of software licensing.
Here we can see a server running some license management software. In another location, we have these colored machines, which represent end-user servers. Each machine has identical hardware, the same processor, the same motherboard, and the same memory. Here we are on machine number 1, our genuine user, activating their new software that they've just purchased. For the purposes of this demo, their details are already filled in. Now they enter a product key. Standard stuff so far. But when they proceed, the system will now enroll the DRAM PUF. What this means is that it will characterize the PUF using all the possible input challenges and get the corresponding output responses. This information is sent along with their user profile to the licensing server, so the provider can use them to verify their machine's identity when they use their software. From the user's perspective, it's just a normal installation. Here's the key we expect to get from the user. This key is never stored on the user's machine. It's generated from the user's hardware using the challenge provided by the licensing server. Now we can see the user running their software. It populates their normal license details. At this point, the licensing server will send a challenge to the user system, and their system will run this challenge through the PUF to generate a response dynamically from the hardware. This response will be compared to the expected responses gathered during the initial installation, and because this is the genuine system, we'll get a match, allowing their software to be activated. And you can see their license in the top left corner is now active. Now we'll move to another machine representing an adversary. The owner of machine 2 has managed to obtain a cracked copy of our software. They've even gone to the trouble of building an identical server, just in case. Will it fool our system? Let's find out. Nice try, but it hasn't worked. Why? Remember, the PUF response is generated from the user's hardware on the fly. Our adversary's memory modules had different low-level variations, and therefore they generated a totally different response, alerting the license administrator as we just saw. To illustrate, let's look at the two different PUF responses. Here's the value stored in the licensing server, originally generated from our legitimate user's hardware, and here's what the adversary system generated, even with their identical setup. Totally different. So here you can see a way that we can use a PUF to identify machines based on their hardware in a way that is very difficult to circumvent, and which only uses the commodity hardware already present in the system to do it. This is just one example of how such hardware-based identifiers can be used to add a further layer of security and trust into a system. Thank you for listening.